Hello students, welcome to Sri Siddheshwar Women's College of Engineering, Solapur. We are dealing with now functions of complex variables, integral calculus part. From this unit, now we are going to discuss Cauchy's integral theorem and Cauchy's integral formula in this lecture. So let us first see Cauchy's integral theorem. The statement of this theorem is, if f of z is an analytic function and f dash of z is continuous at each point within and on a simple closed curve C, then integration over C f of z dz equal to 0. Here from this diagram it is clear that this is a region R. This region R is bounded by the curve C. Along this curve C, integration of the function f of z with respect to z is 0. So this is Cauchy's integral theorem. Extension of this theorem is also available. If f of z is an analytic function in the region R between two simple closed curves C and C1, then integration over the curve C and integration over the curve C1 of this same function f of z is same. Here it should be dz. So we are performing the integration with respect to z only along these two different curves. The curve C, just check its direction. It is in anticlockwise direction and C1 is in clockwise direction. But the integration along these two curves is same for the same function. This is nothing but the Cauchy's integral theorem. Now let us see Cauchy's integral formula. If f of z is analytic function, is analytic function at each point within and on a closed curve C, and if A is any point within the curve C, then 1 upon 2 pi I integration over C of f of z upon z minus A dz is equal to f of A. So this integration is nothing but the functional value at z equal to A. If A is a point within the closed curve C on which the function f of z is analytic function. So this is Cauchy's integral formula. From exam point of view, this topic is very important as there will be surely one example, one question from this topic. Now depending on the position of point with respect to the given curve C, the integration value is different. The first case is integration over C f of z upon z minus 1 or integration over C f of z upon z minus 1 bracket raised to n, that is the factor is repeated n times. If see here, this is the point z1, instead of this A we have taken here z1. If point z1 is outside the curve C, then this integration value is straightway 0. Second position of z1 is inside the curve C. If this is the case, then the integration value is either 2 pi I f of z1 or 2 pi I upon n minus 1 factorial n minus 1th derivative of function at z equal to z1. So these two cases are for the single point A or z1. If there are 2 points, that is the denominator is a product of two linear factors z minus z1 and z minus z2, then both these points z1 and z2 are lying outside the curve C, then integration value is 0. But if both the points are lying inside the curve C, the integration exists and it is equal to some constant multiplier k1 into 2 pi I f of z1 plus some another constant multiplier k2 into 2 pi I f of z2. Suppose there are 2 points again, but one point is inside the curve C and the second point Z2 is outside the curve C. Then for this point Z2, the integration value is surely 0, and for this point Z1, the integration value is k1 2 pi I f of Z1. So the final integration value is k1 2 pi I f of Z1. The last case is the vice versa of this case. Suppose Z1 is outside and Z2 is inside, then for Z1 integration value is 0 and for Z2 integration value is simply k2 2 pi I f of Z2. Now referring this integration formula, that is Cauchy's integral formula, and this table, depending on the position of the points with respect to the given curve C, we are going to solve the integrations. So this Cauchy's integral formula helps you to find the value of integration without actually performing the integration or even without applying any integration formula. So let us solve some examples. There are different types of examples where we can apply Cauchy's integral formula. So first, type 1. Here the case 1 where only one point is considered. This point Z1, it may lie inside or outside the curve C. Example first, integration over C z square plus 5 upon z minus 3 dz, where C is the circle mod z equal to 4 and the second curve is again a circle mod z equal to 1. So for these two different curves, we have to integrate this function z square plus 5 upon z minus 3 using Cauchy's integral formula. So this is our standard formula, f of z upon z minus 1, and integration z square plus 5 upon z minus 3 is the actual integrand. Comparing, we get f of z equal to z square plus 5 and z1 equal to 3. So these are the coordinates of this point z1. Now consider the first curve, that is the circle mod z equal to 4. This is a circle with center at origin and radius 4 units. So this point z1 equal to 3 obviously lie in this circle, that is it will lie inside the curve C, and hence integration exists and it is equal to 2 pi I f of z1. So we are having f of z here, replace z by z1, that is z1 equal to 3. So replacing z by 3 in this formula or in this function f of z, we get value of f of z1. Multiply that result by 2 pi I, we will get the integration value, and here we get it as 28 pi I. So in this way, without using a single integration result, you can find the integration just by applying Cauchy's integral formula for the functions of complex variables. Now still there is another curve, that is again a circle mod z equal to 1. So it is a circle with center at origin and radius 1 unit. As compared to this circle, the point z1 equal to 3 lie outside the circle, and hence the integration value is 0 as per the Cauchy's integral formula. So in this way you can find the integration of the given function where the point is lying inside the curve C or outside the given curve C. Let us see one more example. Here integration over C e raised to z upon z minus 2 dz we have to perform, where C is the circle mod z equal to 3 and mod z equal to 1. Here integrand is very simple, e raised to z upon z minus 2. The point z1 is 2 and f of z is e raised to z. Let us consider the first curve, the circle mod z equal to 3. So it is a circle with center at origin and radius 3 units. So with reference to this curve C, the point z1 lie inside the curve C, and hence its integration value is equal to 2 pi I f of z1. Here f of z is e raised to z, and hence z is replaced by 2 to get the value of f of z1. So we get 2 pi I e square as the integration result. Second case, second curve from this example, that is the circle mod z equal to 1, circle with center at origin and radius 1 unit. With reference to this curve C, the point z1 equal to 2 obviously lie outside the curve, and hence by Cauchy's integral formula, its integration value is 0. So here in these two examples we have discussed the case where only one point was there, that is the denominator is having only single linear factor. Now the type 2 examples, here there will be 2 points z1 and z2 and both the points are lying inside the given curve C. So these are type 2 examples. Let us solve one example. 3z square plus z upon z square minus 1, this is the integrand, and the curve is the circle mod z equal to 2. Obviously the factors of z square minus 1 are z plus 1 and z minus 1. So here we get the 2 points as z equal to 1 and z equal to minus 1. Comparing with the standard form, we get f of z equal to 3z square plus z and the point z1 equal to 1, z2 equal to minus 1. Now consider the given curve. It is a circle with center at origin and radius 2 units. Now with reference to this circle with this curve, the 2 points z1 and z2 surely lie inside the circle, and hence the integration at both these points exist. So we have to apply here partial fraction method to separate the integration for both the points, and so that we can reduce this type 2 example to type 1 example and we can apply the method of type 1 example. So here this is f of z and here z1 is 1. This is also f of z again and z2 is minus 1. So the answer is 1 by 2 2 pi I f of z1 minus 1 by 2 2 pi I f of z2. Here we have to perform partial fraction method to reduce this integration to this form. So this part is left to you. Now f of z is 3z square plus z, z1 is 1 and z2 is minus 1. So with these values we get final integration result as 2 pi I by Cauchy's integral formula. Now we will discuss one more case in type 3 examples where both the points lie outside the curve C. Z plus 2 upon z minus 3, z minus 4. Here circle is mod z equal to 1. The points are here z1 equal to 3 and z2 equal to 4. The given curve is nothing but the circle with center at origin and radius 1 unit. So it is very clear that the 2 points z1 and z2 lie outside the curve C or outside the circle, and hence by Cauchy's integral formula we can directly write that this integration result is equal to 0. So if both the points are lying outside the curve C, the complete integration result is 0. Now we will discuss the type 4 examples where one point is lying inside the curve C and the another point is lying outside the curve C. This is not similar to the previous 3 types of examples. So please concentrate on the solution of this type of example. Here the integrand is z plus 3 upon z square plus 2z plus 5. Denominator is a quadratic term. We have to factorize it first so that we can identify the points z1 and z2. So factorizing we get the factors as z plus 1 plus 2i and z plus 1 minus 2i. From this we get z1 as minus 1 minus 2i and z2 as minus 1 plus 2i. This is your f of z, simple function z plus 3. Now we have to check the position of these 2 points Z1 and Z2 with reference to the first curve, that is the circle mod Z equal to 1. Here C is the circle mod Z equal to 1 with center at origin and radius 1 unit. Both the points Z1 and Z2 lie outside the circle. So by Cauchy's integral formula, the integration result is surely 0. Now with reference to the second curve, which is a circle mod Z plus 1 minus 2i equal to 2, is nothing but a circle with center at some other point A, which is equal to minus 1 1 and radius 2 units. So with reference to this circle, the point Z1 lie outside and the point Z2 lie inside this circle mod of Z plus 1 minus I equal to 2, and hence here the integration calculation method is different. Here we have to first rearrange the terms given in the integrand. So what we have done here, the point Z1 lie outside. Point Z1 is nothing but minus 1 minus 2i. Its corresponding factor is here Z plus 1 plus 2i. So we have to write this term in the numerator without changing its value. That is, it should be in the denominator, but it should be written along with the numerator, and the denominator should contain the factor which is related with the point Z2, which is lying inside the circle. So you have to rearrange in this way so that the point which is lying outside will have the corresponding factor in the numerator without changing its value, and hence applying the Cauchy's integral formula with the modified f of z, we get the integration result. So here now f of z is not z plus 3 only, but it is z plus 3 upon z plus 1 plus 2i, and hence we have calculated here 2 pi I f of z2. So f of z is here the complete numerator term, that is z plus 3 upon z plus 1 plus 2i. Now you have to put here z2 point. So with simplifications we get the integration result as pi into 1 plus I. So in this way there are 4 types of examples where we can apply Cauchy's integral formula. Actually these are nothing but the 4 cases where we can apply Cauchy's integral formula. These cases are based on the position of the points with reference to the given curve C. If the curve is different, obviously the position of the points will get changed and you will get different answers. So please note carefully that here the curve, its equation and the position of point with respect to that curve is very important to apply the Cauchy's integral formula to find the integration results. Thank you very much for listening patiently. Have a nice day.